As I mentioned, here in this session we will be discussing about the elementary design of two different types of dryers. One is the cross circulation dryer, that happens in case of tray dryer. So, we will focus on this batch mode of tray dryer, and another is the through circulation drying in case of a packed bed. So, you see, so point of discussion is drying calculation, right. The first one is cross circulation drying, right. So, you see that we place the solid in a tray which has got a thickness of LS, and there is another tray here, right. So, the inlet gas, hot gas which is circulating, has got a humidity Hi and its temperature is Tgi. The solid surface temperature is Ts, right. Here also we will have the convection, right. So, Ls is the thickness and this has got Ks. The thermal conductivity of the solid is Ks and this is the gas out, right. So, now primarily we will consider that case 1, the gas temperature does not change along the length of the tray. Right. So, the outlet temperature is also Tgi, right, and this happens if the length of the tray on this side it's small compared to the velocity of the gas is high, right. So, first you see we have convective transfer here from the top, but from the bottom as well we have a combined convection plus conduction through it, right. So, here we have conduction. So, this heat transfer coefficient is Hc, and here if this for the convection it is Hc, but for conduction the resistance we can write as this Ls by Ks, right. So, at the bottom convective and conductive resistances act in series. So, 1 by Hb, where Hb stands for effective heat transfer coefficient at the bottom. This overall resistance must be equal to the sum of the convective resistance plus conductive resistance. Okay. So, you can get the value of Hb if I know Hc, Ls and Ks. Now, you see generally this Hc, it is related to the empirical equation through an empirical equation, right, where to this Gs prime, let us say Gs prime is the mass flow rate per unit area. Like as it moves, you see that the trace looks like this, right? The trace in an isometric view looks like this. So, the area we are talking about for gas flow is this area, right? So, through this area the gas actually enters and its inlet velocity is perpendicular to this area, and let the mass velocity is average velocity multiplied by density. So, that is Gs prime. So, Hc we can find out the coefficient. There is an empirical correlation 0.0204 Gs prime to the power 0.8. It is very similar to C dot dot A equation for convective heat transfer coefficient in turbulent regime through a pipe, right. So, you see we have got Hb. Now, in order to calculate, we have, what is our primary objective? Our objective is to calculate Nc, and Nc is equal to Ky prime into Hs minus H, or Hi rather, right, Hs minus Hi, where we assume the solids to be covered with a thin film of liquid, right. Now, how to calculate Hs? We have to know Ts, the solid surface temperature, right, but that we cannot measure. So, the point is we have to generate an equation. One equation is known from saturation relation, a saturation plot, psychometric plot, a psychometric chart. We have Hs as a function of Ts, that is known to us, right. So, we must derive another equation, and that we can derive considering the equilibrium between the latent heat transfer and the sensible heat transfer, right. So, latent heat transfer from the solid to the gas is equal to Ky prime into Hs minus Hi into lambda W, right. Now, sensible heat transfer, you see it's that transfer is taking place from the both sides, and we have evaluated the respective heat transfer coefficient. From the top it is simply the convective heat transfer coefficient, from the bottom it is the effective heat transfer coefficient which is arising out from conduction and convection. So, overall a total sensible heat transfer it's equal to Hc plus Hb into Tgi minus Ts. Okay. Now, these two we will simply equate at equilibrium. So, at equilibrium we have Hc plus Hb into Tgi minus Ts is equal to Ky prime Hs minus Hi into lambda W. So, you can further write this as HC 1 plus HB by HC TGI minus TS equal to Ky prime HS minus HI into lambda W, and can be further written as HS divided by Ky prime 1 plus HB by HC into TGI minus TS Ky prime HS minus HI into lambda W. Now the point is, we don't have to, here this Ky prime, we don't have to use any correlation for Ky prime, because for air water system, HS divided by Ky prime equal to Cs, that is a humid heat, right? So once we know this humid heat, so immediately we get this Cs into 1 plus Hb by Hc into Tgi minus Ts is equal to Hs minus Hi into lambda W. So this is altogether a new function, say it is f1 of Hs and Ts, right? So we have equation 1, we have equation 2. So from equations 1 and 2 we can solve for Hs and Ts, right? So once we know that, obviously NC Ky prime into Hs minus Hi can be solved, right? So once we solve this NC, my problem is over, because now we know it's a batch mode of operation, right? It's a batch mode of operation, and we have this for linear falling rate period, which indicates that the entire falling rate curve or falling rate period is linear, and we have solved for this batch time, right? For the batch time we have solved, and that was equal to theta equal to Ws ANC Xi minus Xc plus Ws by A Xc minus X star divided by Nc into ln of Xc minus X star by Xf minus X star. That was the equation. So here for the present case, we can simply substitute it, this k into this ys minus y, that you can simply write here, and we can get the theta is equal to 1 divided by Ky prime Hs minus Hi, Ws will be here, A will be here, into Xi minus Xc plus Xc minus X star into ln of Xc minus X star divided by Xf, which is the final this moisture content we can solve, because we have already solved for Hs, right. So that's the case of this calculation for cross circulation drying. However, there may be, if we drop the assumption, the gas temperature does not change. If the gas temperature changes, what will happen? Okay. So we'll go for case 2, where the gas temperature will change from TGI to TGO, but we don't know what is the value of TGO here. Solid surface temperature remains constant because we are intending to predict what is the value of constant rate drying, that is NC, right. So if temperature changes, the first task is to predict what is the outlet temperature. What is the outlet temperature of the gas, right? So this is case 2. And let's say this is the width W and this is B, right? So case 2, gas temperature changes along the tray. So we have to go for a differential analysis. See, this is, if we consider Z, here we consider a segment. So let me draw it. It will look like this. Right. So this is the tray. Here we have the solid. So this is Z, and we consider a strip-like section between Z and Z plus dz, right? And gas temperature here, the humidity is Hi, its temperature is TGI. So if the gas temperature changes, we have to go for a differential analysis. We have to use differential analysis. To predict the gas temperature, the outlet gas temperature. Right. So you see over this section, if the enthalpy change will be Cs, humid heat, into Gs prime into B into W. This is the mass flow rate multiplied by specific heat into dTg. It's decreasing, right? And it's decreasing because it's delivering the heat to the solid. So it is Hc, we consider only Hc that from the top. Then this W into dz into Tg minus Ts, right? So W cancels out. So dTg by Tg minus Ts integral from Tgi to TGO minus Cs into B into Gs prime is equal to L, where L is the total length of the plate. And this from here we know it's W and this gap is B. So if we integrate including the negative sign, so Gs, Cs into B, and there will be Hc of course. So Hc into ln of Tgi minus Ts divided by TGO minus TS. Okay? So you have a kind of NTU HTU formulation here. The total length of the tray is equal to HTG into NTG, where NTG is basically equal to ln of TGI, or rather we can think that, yeah, TGI minus TS divided by TGO minus TS, which is L divided by HTG, right, which is L divided by HTG. So if this is the case, yeah, so you see, then TGO minus TS divided by TGI minus TS is equal to exponential of minus L by HTG. So 1 minus this TGO minus TS divided by TGI minus TS, and that's equal to TGI minus TS minus TGO plus TS. So numerator will be TGI minus TGO, denominator will be TGI minus TS, is equal to 1 minus exponential of minus L divided by HTG. So immediately we have the measure of this outlet temperature, because we know what is the inlet temperature, and TS we can actually solve right. So TGI minus TGO has been solved. So basically you have this expression in terms of TGI, and the solid surface temperature will be a function of this HS. See, একটু আস্তে করবেন, হ্যাঁ এটা কি দেখবেন। So here once we have this, first the question is how to solve for TS, right. So in order to solve for TS, you see that we have to go differently. What is that? We should develop, here we have three unknowns, TGI, TS and HS. So we can write the same equation as minus of CS into GS prime into B into W into this DTG, or rather B into W into this CS we drop, GS prime into B into W into plus DH, it's a mass transfer equation, KY prime into this HS minus H into W into DZ. So you can integrate, and again, see, I am not going this entire exercise, you can integrate and predict a relation between HO and HI, right. Inlet and outlet enthalpies you can actually relate, okay. So once we have this relation, we are introducing another new variable which is HO. right. So HO is another new variable. So we have two equations only, and additionally we have the equation HS is equal to a function of TS from the psychometric chart. Additionally, another equation, this I think here okay, let's drop this specific perspective. Let's drop this perspective. Instead, let's go for an understanding. This is a theoretical calculation that we know TS, okay, because otherwise the things will be extremely complicated. So if I know TS, now we are able to predict what is the outlet temperature. Now once we have predicted the outlet temperature, NC we can write as GS prime B into W into CS into TG I minus TGO, right, divided by A into lambda W. Here the solid surface temperature must be known, otherwise we cannot apply this specific technique what I am discussing, right. So that is NC. So NC is known, so you can again calculate theta C. So theta C will be the moisture removed divided by A into NC. Now moisture, amount of moisture which has been removed over the constant drying rate is A into rho S into LS. Rho S is the effective density, excluding this or it is the density of dry solid, right, A into rho S into LS, the quantity of moisture to be removed, right. Now this multiplied by Xi minus Xc, right, that is the total moisture to be removed divided by ANC. So A cancels out, so simply if we substitute the value of NC, we will get theta C. So we will get the value of theta C, and once theta C is known, theta equal to theta C and theta F, we will use the same equation as we have used previously. But what is the point, important point to be noted is this energy balance, right. This energy balance we must focus, and actually I am not asking you to remember all the procedure what we are using, but this is the way how we can approach an unknown system and can write the equilibrium relations, and from there we can generate the system equation, right. So next is a case of through circulation drying, and again in through circulation drying, see what happens in case of through circulation drying. See, we have a bed of solid, right. Now here with a given humidity, so this is a case of through circulation drying. So HI, TI, and here it's moving out with HO and TO. So initially the bed or all particles or all solid particles initially have unbound moisture. That's our assumption, right, and generally that is the case. So initially everywhere we have unbound moisture. Now, as we continue the process, what will happen? Over some region, you see, it's an intermediate state. Over some region, which is, let's say, zone 1, here the unbound moisture, all unbound moisture will be removed and bound moisture removal will be taking place. So, this is bound moisture removal. After that, there will be another region where we have unbound moisture removal. That is zone 2. And the next half of the bed, where the air as it's moving down the bed, right, it is acquiring moisture and it becomes saturated. So, part initially will be there, a region with original moisture content. That is the progress of drying. Now, with time what will happen? The zone 1 will move downwards, zone 2 will move downwards, zone 2 will finally eat up the zone 3, and in the later stages, zone 1 will actually penetrate into the zone 2, and finally entire bed will operate with the bound moisture removal zone, which is alternatively is basically the region where we have unsaturated surface drying. So, that is the entire case of through circulation. Here we can perform a tentative calculation regarding the bed height, considering this operation is taking place in zone 2, because it is giving you the constant rate period. Right. So, Gs prime, it is the mass velocity or mass flow rate per unit area, right. So, Gs prime into dH will be equal to Ky into A bar, which is the available surface area for drying, dz into Hs minus H. Just like it is the stripping kind of stripping operation, right. So, Gs prime into Ky prime A bar integral Hi to Ho dH divided by Hs minus H is equal to the total height, right. So, the gas density change, gas humidity changes from Ho to Hi, and if I integrate, it will become ln of Hs minus Hi divided by Hs minus Ho. This is the NTU equivalent term multiplied by Gs prime by Ky prime A bar is equal to Zt. So, this is what we have used. We have used NTG and this is HTG, and that is equal to Zt. NTG and HTG, that is equal to Zt. So, Hs minus this H0, the same technique as the temperature we have used, Hs minus Hi equal to exponential of minus Zt divided by HTG. So, we have to get the Ho. So, how we can calculate? 1 minus so this becomes Ho minus Hi divided by Hs minus Hi equal to 1 minus exponential of minus Zt divided by HTG. So, you have got what is Ho minus Hi, right. So, Ho minus Hi, we have calculated. Now, the bed has got a unit per unit cross sectional area or per unit volume, it has got drying area of A bar. Now volume is LS into 1, right. So A bar into LS into 1 into NC must be equal to GS prime into HO minus HI, simple balance equation. So where from we can get NC equal to GS prime HO minus HI divided by A bar LS. So NC has been obtained, right. So once NC is obtained, the moisture to be removed in the constant rate drying period, MC, is equal to LS or rather ZT. So here we should not write LS, this is ZT, we have a change in notation, ZT, this is ZT as we have used there. So MC equal to ZT into the volume, ZT per unit area, right, into this rho S. But note that here we have to multiply it by 1 by epsilon, 1 minus epsilon. Epsilon is the void fraction in the bed, right. So ZD into rho S is the density of the solid. So ZD or rather ZD into 1 minus epsilon is the solid volume, multiplied by rho S is the weight of the solid, dry solid, into Xi minus Xc is the amount of moisture removed. So theta C we can calculate as MC divided by NC into A bar. Or this, NC has been calculated, A bar into this ZT, right. So in the same sense, there when we are thinking about this tray of the solid in cross circulation drying, we should multiply it by 1 minus epsilon. Otherwise, LS there is the thickness, right. LS is the thickness, A is the area. So ALS is the total volume, it is not the solid, dry solid volume. Dry solid volume means it must be multiplied by 1 minus epsilon multiplied by rho S, the dry density of the solid. So that multiplied by Xi minus Xc. So this is the very basic idea regarding the design of the industrial dryers, right. And lastly, we will discuss about a simple material balance in a continuous dryer. Now let us say it is a counter current mode. Let me draw the diagram. So here we have the dryer. So in the schematic we have the dryer, and let us say it is a counter current continuous dryer, right. So we have, let Q represents or Q dot represents the heat loss, we have the air flowing in this direction or the gas whatever, and solid in this direction. Now here it has got GS as a dry air flow rate, right, per unit hour. H, this side is say 2, this side is 1. So it is GS H2 into Tg2 and humid enthalpy Hy2. Here it will be GS H1, Tg1 and Hy1. Now the solid LS, dry solid flow rate. Then we have this TS or TS1, its moisture content X1 and solid humidity HS1. Here we have LS, TS2, X2 and HS2. So first it will be simply balanced between water. So GS we can write, the air is gaining water, so HY, H1 minus H2, right, must be equal to LS into this X1 minus X2. Okay. So GS into H1 minus H2, LS into X1 minus X2. Now regarding the energy balance, we have GS, what is the inflow? GS or rather what is the change of enthalpy of the gas? It will lose enthalpy where the solid will gain it, right. So GS into HY2 minus HY1 is equal to LS into HS2 minus HS1 plus Q dot. So that's the energy balance. HY you know that it is CS into Tg minus T naught plus lambda naught into H, whereas HS we can write as CS, or rather it is CS. These CS will be, or rather what notation I have used? Or rather CPS, dry solid specific weight, Ts minus T0 plus X into CPL into Ts minus T0. The solid contains liquid water, right, and that's why it should be this simply X it should be X into CPL Ts minus T0. So this is a gross energy and material balance what we can write for a continuous dryer. Now we have discussed about the two different dryers. One is the tray or the cross circulation drying, and for the cross circulation drying the first case is industrially more probable because the gas flow rate is pretty high and the temperature of the gas doesn't change much. Okay. So for that we have got the rigorous calculation. In the second case where the gas temperature is changing, we have to know the solid surface temperature, otherwise we are having three different variables, right. So it is this TGO, then TGI and TS and HS, right. So we have to know the solid surface temperature, otherwise we have to go for complex, incorporate more equations. But that's not the point. The point there was how to calculate the outlet gas temperature in terms of this inlet gas temperature and solid surface temperature. And from there we have calculated basically the NC, the constant rate of drying, and theta C also, right. So next we have considered this true circulation drying in this packed bed mode, that's also a batch, but we have considered only the unbound moisture removal over this constant rate period, over this constant rate period. So though the bed may operate initially, the entire bed will undergo for this unbound moisture removal, right, but unbound moisture will be removed after some interval of time. So the topmost region of the bed, if I have a delivery of air from the top, will be now undergoing after some time, will be undergoing this bound moisture removal stage, whereas the latter stage will be the unbound moisture removal, and finally when the air will be saturated, the moisture content will be same as that of initial. But we have seen that zone 1 will proceed or penetrate into zone 2, whereas zone 2 will penetrate into zone 3, right. It's pretty obvious, but note that the zone boundaries are not sharp, they are diffuse. So in that case the unbound moisture removal zone will finally occupy the zone 3, and in the latter stage zone 1 will occupy this entire area of the zone 2 or volume of the zone 2, right. So, we have considered the bed height design based on entirely the unbound moisture removal where the constant rate drying is feasible, right. So, for that we have used the material balance, so and that there we need this A bar data, which is a specific mass transfer surface area per unit volume of the bed, and from there we have predicted that what will be the outlet humidity of this gas stream provided we know the height, right, this bed height or the tower height we know. So, there we have again we have calculated HO, and from that HO we have calculated NC. NC is basically it was based on that total amount of the moisture being removed divided by the specific moisture. This difference of HO and HI, this is simply a material balance over the bed we have used, because this NC into A bar into ZT, that is the total amount of moisture removed, which must be is equal to the respective moisture gain rate by the gas flow, and that is GS prime into this HO minus HI, right, into ZT. HO minus HI into GS prime, and that must be is equal to A bar into ZT into NC, and from there we have calculated NC. And once we know this NC, now how much moisture is being removed over the constant drying rate period, that moisture fraction, moisture amount we know, that is Xi minus Xc, and that multiplied by the weight of the dry solid, which is basically this Zd into 1, that is the overall bed volume, into 1 minus epsilon into rho s. Rho s is the density of the dry solid. So, once we have MC, once we have NC, so MC divided by A bar into NC will give you theta c, right. A bar into NC into ZT will give you the theta c, that calculation has been shown. So, these are all tentative calculations, right. These are all basically tentative calculations just to actually have a practice of how to actually write the system equation for a case where we have simultaneous heat and mass transfer. It may not be drying, it may be something else. So, it may be an unknown case of mass transfer. So, even in that case, what should be my way of approaching the thing, how to approach that problem and solve the design of the system equation. That is the basic idea of this session, right. It is not only exclusively about drying. We have taken drying as a simply case study, and from there we have tried to derive the relation. So, and finally we have done this continuous dryers, energy balance and material balance. Okay. That is also very, very common, right, very simple, but the fact is this strategy of incorporating the water's enthalpy in the overall solid enthalpy, right, and because this 1 kg of dry solid is associated with x kg of liquid water, similar to humidity study where we have calculated formally what is the humid enthalpy. So, based on this we can write the balance and we can solve the problem. So, that is all about the drying. In the next session we will discuss about the very fundamental mass transfer operation, that is distillation.